Okay, so let's now begin lecture 16, random processes. This is the second in a series of lectures on random processes. Yesterday in lecture number 15, I discussed random processes and Markovian processes, population and sample, and random variables. Also, I did PDF and an example on variance, covariance, and correlation. So this was covered from random processes to correlation in lecture number 15. So today I'll start lecture number 16 and I'll look at random numbers. How do you sample from standard PDFs and how do you sample from non-analytic PDFs? How do you measure the distance between two PDFs? And that is the Kullback-Leibler Divergence. And then look at some very fundamental laws in probability, like the law of large numbers, and then the central limit theorem and Chebychev's inequality. So all these are the foundations for a stochastic approach. And so I think it's really important to get to know all this before we move on to Monte Carlo simulation. Okay, so that's my name and personal email and official email and personal website. And as I said, I'll be happy to get your feedback and answer any questions on my email, or if you would like to leave any comments on the YouTube channel. Okay, so let's begin formally. Let's come to random numbers. Now, random numbers are random, so that they do not follow any algorithm. So since we cannot produce random numbers which do not follow any algorithm, so what we study are not really random numbers, but they are pseudo-random numbers. So we study random numbers which can be generated from some algorithm because we've got computers, so we have to put in some algorithm. Now, if you want to look at numbers which are truly random, then you have to look at some natural phenomena such as radioactive decay. So from what I know, there are three broad classifications of random numbers. There are truly random numbers, there are quasi-random numbers, and there are pseudo-random numbers. And what we use in engineering are mainly pseudo-random numbers. So I'm not really going to get into the fine pure mathematics of random numbers and quasi-random numbers. So for my use, pseudo-random numbers are good enough because I need an algorithm which I can put in a computer program, and I can start generating random numbers, which of course will have some period. As you'll see, they will have some repeatability, but they should be so big that they do not reproduce themselves after 1,000 or 10,000 or 50,000 or 100,000 histories. So they should be things which have not occurred before. And these days, because we've got big hardware, so that's no problem. But in the early days of computing, it was a problem. And if you've seen that movie on Professor Nash in Princeton, A Brilliant Mind, so random numbers were very much the focus in the Second World War. Because messages were sent, even now, WhatsApp, Yahoo, Gmail, they all use random numbers to convert your message into a code which cannot be broken by others, and so you have some security of your conversation. Okay, so the number of random numbers, how many random numbers that you can draw from a population is of course finite, though large. So you need to sample from a population, and you must make sure that they truly represent the population that you are looking at. For example, if I am trying to get the average age of people in a country, then I cannot take all samples from primary schools, because even though I may get a very small variance, but I will not get an accurate result. So to get an accurate result, you have to take a sample which represents the population. As I told you in the previous lecture, the exponential PDF says that the small numbers are more important and the big numbers are less important. If you take some other like x square, then x square will tell you that big numbers are more important. So you have to see the physics of the problem that you're solving, that what area, what region, what part of phase space, which we were discussing, R omega et, what is important and what is not so important. So take samples in the region which is important. So in this lecture, we are going to generate random numbers. We are going to compute their means and variances. And the correlation coefficient, we can also look at between two random variables. So this is what I told you, exponentially distributed random variables from Matlab. This is the graphical user interface. This I think I did in the previous lecture. Okay, so let's start this from here. So now the Matlab functions which generate random numbers, the three most common ones that people use are the uniform random number, for which the function is RAND rand. The second is the exponential random number, which is XRND. And the third is the normal random number, the random number taken from a normal PDF, which is called rand-n. So Matlab gives you rand between 0 and 1. It gives you an exponential random number, and it gives you a random number from a standard normal distribution, meaning a normal distribution which has a mean of 0 and a variance of 1. Okay, so one of the oldest and most reliable methods used for generating random numbers is the linear congruential random number generator. Now you can see that this is what I meant by an algorithm. So here's an algorithm that you've got a SK. So you can start with k equal to 0, and that's called the seed. So you start with a seed and you get S1. Then you put S1, you get S2. Then you put S2, you get S3, and you go on and on. Now G, C, and P, these are all numbers. P is 2 to the power m. And once you get Sk plus 1, then you can divide it by P, and you get the random number, zeta of k. So here S0 is the seed, G and C are multipliers, and mod P implies the remainder after division by P. For example, if you divide 4 by 2, so you get a remainder of 0. If you divide 5 by 2, you get a remainder of 1. So this is the remainder part. The Matlab command for mod is, for example, for this thing would be mod 4, 2. Now, if you look at the early days of computing, this was a big there was a big effort that went into ensuring that the hardware and the software matched and produced a high period. So the integers determine the period of the numbers, in other words, their repeatability, and they also depend on the computer hardware. For example, a large value, n is about 36, ensures a large period. The Los Alamos Monte Carlo code uses m over here, m is 48, giving a period of 10 to the 13. And they use g as 5 to the 19 and c is 0. So when c is 0, it just becomes a multiplier over here. So these limits are dependent on the word length of a computer. Now you don't have to worry about the hardware and the software, because the codes these days have very good random number generators. Now, just to satisfy yourself, here's a little Matlab program I put before you that just put a seed of 1 and take the value C is 47, P is 100, N is 100, and let's generate capital N, let's say, is 100. So let me generate 100 random numbers for you. And just to doubt the system, let me make 5 bins, and each one is of equal width. So the width of the first bin is 0.2. It goes from 0 to 0.2, second goes from zero point 0.2 to zero point 0.4, then zero point 0.4 to 6, then 6 to 8, then zero point 0.8 to 1. And let's count how many of these 100 fell into each bin. Now with this random number generator, this one that you can see, the linear congruential random number generator, so the one that I showed you up in the previous slide. So with this, I get a count, a perfect count that 20 went into each bin. So it's a pretty powerful generator. Now, when C equal to 0, the random number generator is called a multiplicative congruential generator, MCG, or the Lemmer random number generator. When C is not equal to 0, the generator is called a mixed congruential generator. And the period of the numbers that you generate depends on the combination of values as shown over here. So if you take a seed of so much and the G values and C and P values, you can get a period of 20. Now I've purposely taken small to show you that, let's see if I've shown them over here. Okay, so I haven't showed them over here, but what I do is, and what you should do is run this on Matlab. Now, if you remove this semicolon over here, then you'll be able to write the numbers. So of course, if you have 100 or 1,000 numbers, then you won't be able to see things which will make sense. So do this when you have a small number of random numbers. And just satisfy yourself that when you take these combinations, then you actually get numbers repeating themselves. So the first number should be same as the 21st number. The first number should be the same as the 7th number. The first number should be the 3rd and 5th and 7th, etc. Now, here's a mathematical point that when you generate pseudo-random numbers, then you leave holes in between, which is not good because that means you're not sampling space uniformly, which you should be doing. So there's this neat theory in mathematics, which and I remember a paper by Sobol, S-O-B-O-L, an excellent paper, which tells you how to generate quasi-random numbers. And if you use those for numerical integration, you get higher efficiency. Okay, so these are two exercises I want you to do yourself. First, go to Matlab, use the rand function, generate 100 random numbers, check their distribution. Use the tick-tock functions to get an idea of how much time does your laptop take to generate 1,000,000 random numbers. Okay, start with 10, 100, 1,000, 10,000, 100,000, 1,000,000. See how far you can go. Can you go to 10 million? Okay, then you generate a set of 1,000,000 uniform random numbers. So generate a pair of random numbers. Why pair? Because we're going to look at a unit circle, which is x squared plus y squared is 1. Now, if you draw a unit circle like that with radius 1, then any point in the circle, you need a point P needs an x and a y. So let's generate, now these are naturally between 0 and 1. So if you take a unit circle of radius 1, of course, you'll get a number zeta 1 between 0 and 1. This will also be between 0 and 1. So these two define a point in a circle. If you want a sphere, you need to generate the third also. Now, the first thing I'd do if I were you was to test how many of these lie in the first quadrant of a unit circle. So if you've generated 1,000,000, then 250,000 should fall in the first quadrant and similarly in the second, third, and fourth quadrants. Now estimate pi. Pi is such a fascinating number, going back to the time of the Greeks BC. So they said that it's, they noticed that things in the heavenly bodies look like circles. And so they must have drawn a circle with a thread or a rope or whatever they had, and they must have opened it, and they divided the diameter with they divided the circumference by the diameter, and they got a number. And that number is what they called pi. And so they must have done that for small circles and big circles, and they must have seen that, they were getting the same value of pi for small circles and big circles. So they said that this is fascinating and this looks like some universal constant. And they said that if the value is 22/7. Now, when we came to school, we found out that the teachers told us it's 3.159. Then we found out it's 3.14159. Sorry, in school it was 3.142. Then high school it was 3.14159. And I used to get confused because every time my teachers would tell me that it's not 3.14, it's 3.159. When I went to university, somebody told me, I think it was in my first semester as a BS student, or I think it was in A-levels, when we were told that pi is not a number which finishes after 4 or 5 decimal places, it goes on and on. And the best value for pi is that the tan of pi over 4 in radians is 1. So the proper definition of pi is 4 times the arctan of 1. So here it is, 4 times arctan of 1. So what I want you to do is see how many points fall inside the first quadrant. And you know that the area of a circle is pi r squared. So if you put r equal to 1, so the area of your circle should be pi. So the area of the first quadrant should be pi over 4. So if you make a square around the circle and you say how many are falling inside the circle and how many are falling outside the circle but inside the square, then you would get an idea of the ratio of the areas of the circle and the square. So I want you to do that yourself and try to estimate pi from there. Okay, now let's say that you have a PDF. And for example, I know that there are so many like that, so many like that, and so many like that. And now I want to pick out of the population, I want to pick 10 people out of 1 million people. And I want to pick out those 10 people who represent those 1 million people. I do not want to do a calculation with 1 million people. So, well, 10 is a very small number. So if I had a million people, maybe I'd take a sample of 1,000 to start with, and then maybe I'd go up to 10,000. So let's see how you can, this is called sampling. And sampling is vital to everything we're going to do, because step 1 is to be able to get a sample. So sampling can be carried out from either a discrete PDF or a continuous PDF. And you could do it by the direct method if you can integrate the PDF and get the CDF. If you cannot do that, then there's a rejection method which can be used. Okay. So again, start with a simple thing. Let's start with the uniform random number where small f of x is 1, then big F of x is x in this range and 1 beyond this range, as I said in the last lecture. Now, a simple proof that we're going to do is conservation of probability as we move from one variable to the other. So let's say that I have 2 random variables, and I'm going to keep an open mind now. I don't know what x is going to be, I don't know what y is going to be. So let me just talk in general terms that I'm going to consider 2 random variables, x and y, each with its own PDF. So I'm going to call the PDF of x fx, and I'm going to call the PDF of y gy. So then what I'm going to say is that I'd like to work in the x variable, and you might want to work in the y variable. Just like in school, some of us worked in the energy variable, some of us worked in the speed variable, and we said E is equal to half mv squared. So we said dE and dV are related to each other. So now I'm going to call this a conservation of probability. So let me use this conservation of probability, and let me do this, that for x, let me put small f, and for y, let me put big F. I don't think anybody should have any objection. So I'm going to put the PDF as one random variable, and I'm going to put the CDF as another random variable. And that's quite smart, because there's a relationship. You know that capital F is the integral of small f over dx, small f dx over the limits, which means that since differentiation is the inverse of integration. So d by dx of big F is small f. In words, it means that the derivative of the cumulative distribution function gives the probability distribution function. Okay, so if I do this, so this becomes what? So let's not call it f and g now. Let's call it c and d. So c of x becomes c of small f, d small f, g of big F, d of big F, and then I'm going to use this. So that will tell me that the PDF of the CDF is uniform. Okay, let me say that again. The PDF of the CDF is uniform. The PDF of the CDF is uniform. So what does that mean? The last thing I told you was that the PDF of a uniform random number is 1. And here we get the PDF of a uniform random number is 1. So I can equate the random number with the CDF. And this is the breakthrough. This is the bridge that we're going to cross now. So it is for this reason that big F can be used as a pseudo-random number. So I think that's a big crossing of the river. So let me show you in practice what that means. So let's look at an exponential PDF, again back to the one we considered last time, that f of x is 2e to the minus 2x, and remember the mean value of this is a half. So the capital F of x, in other words the CDF, is 1 minus e to the minus 2x, and you see I can invert it so nicely. So I can have the x out in terms of the big F, and for the big F, I can use the random number. So big F is 1 minus e to the minus 2x, which means x is the inverse of big F. And big F is a function of uniform random number. So small x, the sampled x, is so conveniently minus a half times the natural log of 1 minus the uniform random number between 0 and 1. And this is the great breakthrough I was talking about. So what does this mean in English? In English, it means that if you want to sample an exponential PDF, then all you need to do is take random numbers between 0 and 1 and begin to sample for the variable x. You can take 10, you can take 100, you can take 1,000, you can take million. There's no limit on that. Okay, so now this is a very good exam question. It's when I make your assessments, I'll have something in the quiz like this, because if I give you an easy function, you should be able to integrate it, you should be able to invert it, and you should be able to get something like this. Now, if I do not give you something simple, then it's this section over here. Then that means that sampling from non-analytic PDFs, numerically given PDFs. So I should have had a little diagram over here. But so such a direct inversion, this kind of a direct inversion, is not possible for non-integrable PDFs. So we use what is called a rejection scheme. So if I have a function which looks like crazy, it goes up and down, up and down. So I'll surround it by a big rectangle, okay, which I know is easy to solve. So that's called a simple bounding function. And that function, for example, I'll just say it's a big constant. And I say that if I choose a number, and if the function is less than or equal to c times that bounding function, then I'll select it. Otherwise, I'll reject it. So just common sense. So the picture would have made it clear. But this little exercise, do this please. And I wish I was sitting in front of you in a class. Then I could have asked you what you thought about this. But anyway, do this yourself. And if you cannot, then do send me a message, and I'll give you a little solved problem. Now, the book that you can take a lot of help, let me share the screen of that book. is there's a book, Kalos and Whitlock. So let me just show you that it's a very good book on Monte Carlo methods. It's this book over here. Okay, so this is the book. Let me just show you the cover page. So this is the book, Monte Carlo Methods, Kalos and Whitlock. Okay, and there was a book starting with Spanier and Gelbard. There's there are other good books. There's a very good article written by Professor Dubey in CRC. So that's where I learned my Monte Carlo from. Okay, now let's go back to where I was with you. So let me try to find. How come I can't find my book over here? So let me try to minimize this. Let me try to find my book over here. Okay, so I hope you can see exercise 2.8. Okay, so I hope you can see exercise 2.8. If I haven't goofed up, then you can see exercise 2.8. Okay, so these are the direct and rejection schemes for sampling. This is your assignment, that take fx equal to 2x and try to integrate this and try to get the CDF, try to invert it, and try to sample for x from here. This is a straight line. Second exercise is a little bit more complicated. So it's a normal distribution function. You can see that there's a standard deviation, there's a mean, and there's a constant. So for this, you could use the rejection scheme. You could put a bounding box around it, and you can do it. If you don't want to do it, then you can search the net. There are ways of doing this by taking, I won't change the screen now because I might have lost it. So I'll show you some other time. But you can take two variables and you can sample this. You just have to put r squared and put in terms of x squared plus y squared and do polar coordinates and you get it. Okay, so that completes the bit on sampling, which we'll use a lot in the next few weeks. Okay, now here's a ruler. When you say you want to measure the dimensions of a room, you take a tape and you measure it. Now, when you have two PDFs, what kind of measuring tape do you use? Okay, the measuring tape that you use has something to do with entropy. And entropy is a very old concept in mechanical engineering coming from Clausius. And Boltzmann did a lot on entropy and the minus p ln of p. And you can show it's related to chaos. It's related to thermodynamics. It's a property of thermodynamics now, entropy. So this has been used by, and it's called the Kullback-Leibler Divergence. So if you've got two PDFs, you've got P, which is a true PDF, and you have done a simulation and you get an estimate of Q. So how do you measure okay, let me call it for now a distance. It's actually a divergence. So I'll just explain the difference between a distance and a divergence. Okay, so the gist of the story is this, that if there is a true PDF and there is something that we've got in our simulation, how do we measure the distance between them? So let's write it as D, the distance between P and Q. Now, why is it called a divergence? It's called a divergence because the reference is very important. So if you go from city A to B and the distance is 300 kilometers, then usually the distance from, not usually, but it's always the case that the distance from B to A is also 300 kilometers. But in this case, it's not like that. If P is your reference, then you get a certain answer. But if Q is your reference, then you get a certain other answer. So let's open this term, P of X, the log of P over Q. So when you open, you get this minus sign. P ln of P minus P ln of Q entropy minus something else. So you write this as the H function. Now the H function is the cross entropy, this one. So this is the entropy and this is the cross entropy. The cross entropy is a measure of the inefficiency of our simulation. How bad are we? Because remember when you do deterministic finite difference or finite volume or anything deterministic, then you say that you have a converged solution because you've got convergence, because it doesn't, your answer won't change if you take 100 more steps. Now here in stochastic processes, you never do achieve a final answer. You always go up and down because there's always noise, there's fluctuations. So that is why we have to see that we've achieved stability. So the Kullback-Leibler distance is your metric, it's your ruler. And whenever I do simulations, I always see the cross entropy so that I can tell you that my answer is good. And if I don't get this kind of a convergence, then I should not tell anybody that my answer is good. And why this is so important is because Monte Carlo simulation is an art and a science. The art part of it being that how do you decide what size of sample do you need? So it's intuitive. Now, when you become an experienced person, 20, 30, 40 years, like I've been doing Monte Carlo simulation since I was a master's student in 1980. So I've done 40 years. And so I have a little bit of sense that what should I do and how should I bias, how should I model a source, how many numbers should I take? So then I can close my eyes and say that here's my answer. But I wouldn't recommend this to early users. So in the first 10, 15, 20 years, always see that you do have convergence. So I like to test my Kullback-Leibler divergence for a finite number of bins. So look at these two. So this is for 10 bins. This is for 20 bins. Now, when I have 20 bins, you can see that I haven't really converged. So if you want more detail in your simulation, so you need a bigger sample size. Now, if you had 10 bins, remember in Monte Carlo simulation, bins are so important because you do not get an answer everywhere. You get an answer where you want to get an answer. It's unlike deterministic codes where you get the field function in the entire domain that you're solving it. In Monte Carlo, you do not get the solution in the entire domain. You get it where your detector is, or you get it where a person is standing and you want to estimate the radiation on that person, or you're interested in breeding in some other blanket of a fast reactor. So you focus on that. So you're always focused on something when you're doing a Monte Carlo simulation. You're not wanting a general answer, because that would take too much effort. So there's your ruler by which you can measure how good or how bad your convergence is. Okay, now as I said, I'm going to look at some fundamental probability. Now there's something called the law of large numbers. And in English it says that if random variables were generated, if they were identically distributed, and if you take more and more of them, then the sample mean that you get will converge to something called the theoretical mean. So whatever you're doing, if you take many, many numbers, but with the condition that they are identically distributed, so they're drawn from the same PDF, so then 1,000 is going to be better than 100 points sampled. Now there's a Chebyshev inequality which tells us that if you want to get a good number, then how far is your estimate x from the mean? So the probability that it is greater than k standard deviations away. Now you do not want it to be too close. You do not want it to be too far from the mean. So if this is 3 standard deviations from the mean, I'd say it's a bad answer. So to the probability that it goes beyond what you accept, is going to be less than or equal to the v of x divided by epsilon square, which goes like 1 over k square. So 3 standard deviations, 1/10, 1/9. So, so according to the law of large numbers, if you get x1, then x2, then x3, and then you say I'm going to get a mean value out of this, and I'm going to get a finite variance, then if you're taking the average of all these, which is what we always do, that's how we get the neutron flux in a reactor, that you do one experiment, the second experiment, the third. So these are called stochastic experiments. I think the German word first used by Einstein was Gedanken. Now that's what I heard in my undergraduate. I could be wrong, but that's the word I heard as an undergraduate student, that these are called mental experiments, stochastic experiments. So that's what we do in Monte Carlo. So if you want to get the mean value over here, and you divide it, you take the sum divided by n, how far are you from the mean? You would like to give an answer in the limit of the large numbers, the law of large numbers, that you would like to reach this value, okay? And this is a little exercise for you to do with Bernoulli trials. So consider n Bernoulli trials. If an outcome is a success or a failure, so you can do this. This is a standard problem. So I'll let you do it yourself to convince yourself that what is the estimate of being away so many standard deviations. And here's the application of the law of large numbers. We'll come to all this when we do our assessments and examples. Okay, now here's a standard, here's something with a mean of 0 and a variance of 1. So if I try to pull out numbers from here, and I want to do an experiment, and I see with 100 numbers and 200 numbers and 400 numbers, then how far, what is the probability that I'm greater than 0.1 out? So here the probability is 1, so this is a bad number. So as I come here, so you can see that the number I estimate for the mean, the correct answer is 0 for this distribution function. So so you can see with about 1,000 numbers, I come to a fairly good answer. So Chebyshev inequality gives me a rough rule of thumb. Now let me show you the central limit theorem. The central limit theorem again continues what I was just saying, that if you sample, if you carry out stochastic experiments, you estimate x1, then x2, then x3, and x 100,000, and these are the sum of, then get Sn, which is the sum of n discrete independent random variables with common distribution, with an expected value mu and variance sigma square, then the probability of this sum being n mu away divided by the variance is between a and b, is the probability, is the integral of the PDF between a and b. If I divide this by n, see what I get. I get the mean value that I'm getting from my calculation minus the mean value that should have come, divided by something related to that sigma square. So what you see, that something is a sigma square over small n. So see, there's a relationship between that and what we get. Okay, so this is fabulous. Now, in plain English, that means that whatever the population distribution of the random variable x, whatever the population distribution, if it has a mean and a variance, then the sampled mean x bar will be a normally distributed value as the sample size becomes very large, which means that put in more and more effort and you should be able to be heading towards a normal distribution. The only thing is that you would like that new normal distribution to have the same mean, not to have a different mean, otherwise you would have a biased estimator. So you would like to have an unbiased estimator. However, you would like to reduce its variance, and yes, the variance is reduced by the effort that you've put in. So it's come down sigma squared by n. And this is such a beautiful aspect of central limit theorem, that I'm going to show you this by a little Matlab program, and I would really like you to do it yourself and to satisfy yourself that yes, you've done it. So let's take a random variable x from a population which we don't know. Okay. So let's say that it has a mean value, because usually you don't know what the hidden story is, that what is the population of a country, the population distribution function. How many people are between 20 and 21 years old? How many are between 62 and 63 years old? How many are between 80 and 85 years old? You don't know. So, but you can take a small sample and you can try to reconstruct the population distribution of a country. So take a small sample, not really small, take a good enough sample, let's say 100,000, and get a sample mean of the average value of this x, right? The Sn that I showed you before. And get its sample variance, and if the central limit theorem is correct, then it should be equal to this population variance divided by square root of n. So what I'm going to do with you is, I'm going to give you a population variance, a population whose mean and variance I know, and I'm going to pretend I don't know it. So then I'm going to estimate it. So let's say I know a standard normal distribution with a mean value of 27 and a standard deviation of 12. I'm going to take 36 samples. Why? Because the square root of 36 is 6 and 12 divided by 6 is 2. So I'm going to take that. I'm going to take 36 samples, but I'm going to repeat that 100 times. And this is a problem I saw on the net, aside from Wisconsin-Madison, my own university. And they said that estimate how many people, that there's a PDF, 27 is the mean, and the 12 people, the average is 12. How many people are less than 30 years old? So here's the program. The mean, so rand, the Matlab function gives you a standard normal with a, in other words, a mean 0 and a variance 1. So if you add the mean to that, multiply by the standard deviation, so you can sample the age of those 36 people. And so I put a little counter. If the age is 30, I'm going to, but right now I'm not interested in the age, I'm just interested in that sample variance and the sample mean. So I do this, I get the average of the age that I've just completed of those 36 people. I get from my first batch, I get a sample average, I get a sample standard deviation. I store it, I go back to the loop, I do it the second time, the third time, and the 100th time. And when I do that, I get the sample mean average, and I get the sample mean standard deviation. Okay, now this is a fascinating thing what I'm going to show you. That the population mean is 27, the population standard deviation is 12. So when I took those 36 people and I took 100 batches, see what it mean I got? I should have gotten 27, but since the sample size was not so big, I got 26.8202. And what did I get? The sample standard deviation. Instead of 2, I got 1.84. Not bad, because 12 divided by 6 is 2, so it should have been 2. I made it 100 times bigger, the sample, which means I should increase by a factor of 10, square root of 100. So see, here it was 2, here I got 0.2. So central limit theorem is working. I'm getting a mean value of 27 as I increase the number of batches, as I increase the sample size for the same number of batches. And here I make it 360,000. So notice 2 more zeros here, 2 more zeros here from here, which means 1 more zero divided in the denominator for sigma s, which improves the sigma s from 2 to 0.2 to 0.02. Now, as I increase the number of batches to 1,000, see what beautiful answers I get. So this looks like a 0.2, and this looks like a 0.02. And the mean is so good, it's 27. So yes, the central limit theorem, I tell you, is good. And I'm okay with it. So So now let me quickly wrap this up because this is not. So what I did was the values of pi, I got estimates for pi, and you can see I changed the number of those points, the sample variance, and the time taken was still small. So I played around with lots and lots of values, and I made a little distribution function of what value I get for pi. So for different simulation parameters, see, I'm approaching a normal distribution. So I'm going to give you an answer for pi, which is normally distributed. And as the numbers become bigger, see, my normal distribution is shrinking. And that's a typical characteristic of sampling. Okay, so now, this brings me to the end of this lecture, that in Monte Carlo simulation, we say an estimate is accurate if its mean is close to the mean of the population, which is generally unknown. Precision is a measure. Okay, this is very important. What is a good answer and what is a bad answer? A good answer has to be precise and accurate. So precision is a measure of the spread or the variance of the estimates from which the mean is computed. And an estimate is not good if it is inaccurate but precise, or if it is accurate and not precise. So it is desirable to have an answer that is both accurate and precise. The best MC estimate would therefore have the correct mean and a zero variance. Now that's such a big thing I've said to you, and just imagine I leave you in this with this lecture thinking that can you get a zero variance answer? And if you can get a zero variance answer, then Monte Carlo is going to be so wonderful that I would not have any uncertainty attached with my answer. So think about it. Can we have a zero variance answer? Can we reduce the variance? Can we go on reducing it till we get a zero variance answer? Okay, so I'm going to stop over there, and we stop over here, and I'm going to stop my recording till the next lecture.